Okay, class, today we're going to go through the last part of section 3.2, which is on page 100. And it covers four things. There's two rules about the range rule of thumb. And then we're going to talk about some uh, theorems that were created related to the bell curves and also the skewed curves. All right, so let's talk about first about the range rule of thumb. So there's two rules of the range rule of thumb that we're going to go through. And it is on page 100. And so the range rule of thumb is a crude but simple tool for understanding and interpreting what the standard deviation does. So it's based on the principle that for many data sets, the vast majority, we say about 95%, of the sample values, they lie within 2 standard deviations of the mean. That's standard. We can improve the accuracy of this rule by taking into account such factors such as the size of the sample, how the distribution looks, but we have to sacrifice the accuracy for the sake of simplicity. So we're going to go through those two range rule of thumbs. All right, so the first one is called the range rule of thumb for identifying significant values. All right, so I'm going to share with you in a minute an example of where you would use this procedure. So we're first going to look at identifying significant figures or significant values. We also refer to that as minimum usual, max usual. So we're going to go over max usual, maximum usual, and the minimum usual. And there's two formulas. So the maximum usual is considered to be a significantly high, and here's the formula. So the formula for it is mu plus 2 times the standard deviation. So mu is the mean, and the O is the standard deviation. For the significantly low, we also refer to that one as the minimum usual. So that one's almost the same as the previous one, but instead of a plus, there's a minus. So it's mu minus 2 times the standard deviation. And so there's a scale. There's a scale that we use. So let me show you an example of where this is used. All right, so if you have children, if you have kids, when they're first born, you have to wait a couple of weeks, and then you have to take them to the pediatrician. And so when you take your child to the pediatrician, there's two things that they have to measure, and it's very important. One is the weight, and the other one is the head circumference of the baby, right? So it's the weight is not a big concern, but lately it has, because the moms are not eating healthy when the baby's in their tummy, right? And they're not eating healthy, they're eating junk food, they're eating Takis, hot Cheetos. And so that plays a factor on the kid's weight. But that's not the big concern. The big one is the head circumference of the baby. So when you take the child to the pediatrician, they will record, they'll measure the child, and then they'll show you this. It's a baby blue chart. I don't know if it's changed the color, but it's a baby blue color graph. And they'll have these lines that go like this, the graph, that look like this. So what they do is they compile all the data from the previous years of all the babies, and they record the circumference of the child's head. So there is a minimum and there's a maximum. So this one is your max usual, and this line is your minimum usual. So if your child's head circumference falls within the max and minimum, your child is healthy. So this area here is considered to be the usual, the green light, usual. They're healthy, they're good. However, if your child exceeds the max, there's a problem. Right? The head size of the child is much bigger than the brain, which means there's fluid building up in the skull, and that's a major concern. So you don't want to be in that area. You don't want to be below the minimum usual because the skull is not proportionally growing at the same rate as the brain, and that's a huge concern. So you don't want to be in this area. So the perfect spot to be is between the max and the minimum. So what they do is every year they will get the data from all the kids from the previous years. They'll calculate the mean, and they'll calculate the standard deviation, and they'll enter these two numbers, and that'll give you the max usual and the minimum usual. So just to clarify again, mu is the mean of the population, right? And the O was the standard deviation of the population. Right. So let's do an example. So let's suppose we'll switch from doctor to psychologist, right? So let's say that you work for a occupational therapist company, and you're measuring IQs of children, right? And so suppose, and they're going to give you the mean and standard deviation. So let's suppose that the mean IQ, that's the mean IQ, is 100, and the standard deviation is 15. And I want to construct my chart. Right? So I'm going to calculate what is my maximum usual value, and I want to find the minimum usual. Right, so here's my formula. Mu plus 2 times sigma. Minimum is mu minus 2 times sigma. And we substitute the numbers in. So I know my mu is 100, so it would be 100 plus, I'm gonna have to multiply 2 times, my standard deviation is 15. Right, so I get 100 plus 30, so it's 130. So this is my max usual. I do the same formula, but instead of a plus, it's going to be a minus. So I'm going to do it over here. So that's 100 minus 2 times 15. So that's 100 minus 30, which gives me 70. So there is my minimum, right? So now I'm ready to use my chart. So let's say a child comes in and their IQ is 100. So IQ 100 means that they are in this area, so they are normal. All good, right? When a child comes in, their IQ measurement is 65. Okay, there's a concern because they are underneath the minimum, so that would be unusual, right? Or you can have the extreme. You have a kid that had, like, I believe there was one child, a female in the UK, that had an IQ 146, which is way above Einstein's 146. and she was only 4 years old, that would be considered unusual. So that's how you use it. Based on the information from the previous years, you enter your mean and your standard deviations to produce your scale. Now, if you don't like this scale, you can do a number line. Okay? So you can put your minimum is 70 and your max is 100, right? And you put a little barrier, right? Anything that falls within, in between this area here is considered usual, right? Usual. And anything above or below is considered unusual. So first, a child with a IQ of 65 is considered unusual. A child with an IQ of 100, that should have been 130, right? 130. It's 130. A 100 would fall in the usual, and then if a student had, a child had an IQ of 146, whoa, that's way above the max. So this is the max, this is your minimum. And so that's how it works. So you got to remember, when you're asked to identify significant values, these two numbers will always be given to you to find the usual and unusual. Let me find it. These will always be given if you want to identify significant values. Okay. All right. So that's the explanation of the first feature of identifying significant values. The next one is just another range rule of thumb formula that is used. So in case you are stranded in a desert island, right, and you do not have access to a computer, a calculator, and you are asked to find the standard deviation. So the range rule of thumb, I'm going to put wrangle. Range rule of thumb to estimate the standard deviation. Right. There's a formula that you can use. So formula for it is sigma equals, or I should put not equals, but I should put these little wavy lines. You all know what these little wavy lines are? They go like that. They look like a wave. This is the approximate symbol. It is approximated by computing range divided by 4. You're like, what is the range? You all remember what range is? Range was simply subtracting high value minus the low value. That gave you the range. And you divide it by 4. So that's the formula that you would use to approximate the standard deviation. If you are stranded and you only know the high and the low value, you can approximate it by that. So it is a rough estimation. It's not a precise. It is the value at the end is a rough estimate of the actual standard deviation. And you can test it. There's a problem in the book that asks you to compute the approximate standard deviation of a setting number. So you just have to use that formula to do it. And that's the second and last part of the range rule of thumb. Okay, so the next part is going to have to do going back to our distributions. So there are theorems that were developed that talks about those specific distributions. So the first one that they refer to is called the empirical rule. So let's look at the empirical rule. Show you where it is in the book. The empirical rule. Okay, so the empirical rule is specifically for data, is a rule specifically for data that are bell-shaped. Okay, bell-shaped. So this is how it goes. So I'm gonna draw my bell-shaped curve. I really have to draw it. Nice. I have to leave some space because this graph is gonna go way above what I need to do. Okay, so here's my bell-shaped curve, right? And the theorist said that if you plot all the data that fits a bell-shaped curve, this will always occur. Always. It always occurs. They did it mathematically. They did a proof, and they proved it. So in the middle, right directly in the middle of the graph, right there, is this. You remember what that is? Well, actually, they use a different. They use because they're doing a sample. So you remember what the sample mean was? What was the sample mean formula or notation? It was X bar, right? So this is your mean, right? And so if the mean is there and this graph is symmetrical, that means that the distance from one point there is symmetrical to the other one. So what they do is they add, if they add a standard deviation to the mean, that's an S. Over here on the other side, you got to do the opposite because it has to be symmetrical. Hold on, I'm trying to. Here would be X bar minus S. And so they say that from one standard deviation away from the mean, if you were to plot all the data points, approximately 68% of all the data would fall within that distance. Okay. If we go further and I add another standard deviation, on this side it would be X bar plus 2S. But to make things symmetrical, over here on this side it would be X bar minus 2S. Again, it's symmetrical. So the theory goes that if you extend the distance from two standard deviations away from the mean, were to plot all the data, I didn't draw lines, but that's all right. Try my best. Approximately 95% of the data would now fall within the green box. It's enclosing the red too. So the red is included in the green. And if I go further and I extend it more and I do 3 standard deviations for the mean, so that's x bar plus 3s. And over here, it's x bar minus 3s. The theory goes that if you were to plot all the data, 99.7% of all of the data would fall now within the purple box, including the green and the red. Right? So when we do 1 standard deviation from the mean, that's what these are. They are this distance from the mean from both sides are 1 standard deviation away from mean. And then this area from there to there represents 2 standard deviations away from mean. And then this area here from there to there is how many standard deviations from the mean? 3 standard deviations away from the mean. So you don't have to memorize these formulas. Those are supposed to be S's. You don't have to memorize these formulas. This is not what you need to memorize. What you do need to memorize is you need to memorize these 3 percentages. These are set. You cannot change these. It's been proven that 68% of all the data when plotted fall within 1 standard deviation of the mean when it's bell shape. It's 95%, all the data, about 95% of all the data would fall within 2 standard deviations of the mean if it's bell shape. And then it's 99.7% of all the data would fall within the larger picture if you were to plot all the data if it were bell shape. So these you have to memorize: 68, 95, 99.7. So this is the 3, this is the 2 standard deviations from the mean, this is 1. You have to memorize those 3. Don't memorize these. These are going to be simple. I'm going to show you a way to remember these formulas. Just memorize these 3. Okay, so let me give you an example. So you're going to have to draw a picture. You're going to have to draw a picture of the bell shape. So let me draw another one. And just like we did with the range rule of thumb, with the identifying usual, unusual, max and minimum, material that we covered, you'll have to draw. Okay. Now, again, you're gonna put a line here. They're gonna give you, just like we did with the usual and unusual, min max. You'll be given the mean and standard deviations. That's gonna be given. All right. So let's suppose that we know that our mean is 100 and our standard deviation is 15. Okay, that's given. All right, so what do? Well, I already know that my mean is 100, so I'm going to label that as 100. Okay. Now I have to label my little tick marks after and before. Okay, so knowing that that's my mean, I'm going to use the fact that my standard deviation is 15. So if I want to label these tick marks, I'm going to continuously add 15 as I go and label my tick marks. So you're going to add 15, you're going to add your standard deviation to get to this mark. So if I add 15 to 100, I get 115. If I want to get the next tick mark label, add another 15. If I add 15 to 115, I get 130. And you continue adding on 15 as you go to the right. You add 15. So the next one would be 145. Right? So you add, when you label on the right, you add 15, you add your standard deviation. But when you label these, you do the opposite. Instead of adding 15, you're going to subtract 15. So if I start with 100 and I want to label that tick mark, I'm going to deduct 15 because that's what my standard deviation is. So that would equal what? 85. And I continue subtracting 15. That would give me 70. Subtract another 15. I get 55. And now I'm going to put in my boxes. And you're going to tell me what those box percentages are. Remember, those do not change. They are what they were at the very beginning. So what were they? First box was 68%. The next box is 95. And the bigger box is 99.7%. So you put your mean, you add standard deviations as you go right, you subtract as you go left. Then you can answer questions. So they're going to ask you, what percent had IQ scores between 70 and 130. Right? So you go to your 70, you go to your 130, follow the box. Oh, that box is 95%. So my answer is 95%. That's it. I can ask you, what percent had IQ scores between 55 and 145? Percent. 45. Right, so you go to 55, follow along. It should reach 145. That percentage is in the 99.7%. And I can only ask 3 questions, right? What percent had IQ scores between 85 and 115? 85, 115 falls in the 68. Right. So you're asking, well, what if you ask, what is the percentage of IQ scores that had between 85 and 130? You can't, because 85 and 130 are not symmetrical. They have to be equal distance from the mean. 85 is 1 standard deviation of the mean, 130 is 2. They cannot be. The numbers have to be symmetrical. They have to be equal distance. right? Because it's bell-shaped. It's a bell-shaped curve. So that's the empirical rule. So you have to memorize these three percentages. You will be given the mean standard deviation. You just fill them in. Fill in your mean, add standard deviations as you go along to the right, subtract standard deviation when you go left. Got those, fill in the boxes with the percentages, you can answer the question. Okay, all right, so that's the empirical rule. Now I got to show you another theorem. So this theorem, remember, this theorem is only for bell-shaped data. Now this other theorist, his name was Cheby. I believe he was from Russia, and he did not agree entirely with the empirical rule. So he developed his own theorem. Right? So he said, wait a minute, you got the bell-shaped curve. What about the skewed data? You left out the skewed. We need to, he created something that covers not only the empirical rule, but he also covered the data that are skewed. Okay, so his theorem covers both bell-shaped and skewed. Okay, now, so it's almost like the empirical. So I'm gonna draw another normal curve, bell shape. Okay, and his theorem goes like this. So he agreed that in the middle you have your mean, totally in agreement. However, he doesn't believe that when you mark off the marks on the left and the right, he does not believe that there exists one standard deviation from the mean. Okay. He doesn't believe that that exists. So he removed it. He starts off with 2 standard deviations from the mean and 3. And same thing likewise, because it's symmetrical, right? If this is plus, over here is minus. Three S, not a 5, not 35. These look like 5s, but there are S's, standard deviation. So he doesn't agree that one standard deviations exist. There's one standard deviation away from the mean doesn't exist. Does not exist. So he marks them off. So he starts out with 2 and 3. So in addition to that change, he also believes that the percentage, if you were to plot all the data, the amount of data plotted, the percentage of it is different. He believes that the amount of data that are between the 2 standard deviations is 75%. And from 3 away is 89%. 89. So empirical rule had 3 of them. It was 68, 95, 99.7. Cheby believes there's only 2. It's 75 and 89%. And that's for both bell shape and skewed. So this here represents 2 standard deviations from the mean. And this area is 3 standard deviations from the mean. Right. So empirical rule, you had 3 in the right, 3 in the left. Cheby says there's only 2 on the left, 2 on the right. This one doesn't exist. Empirical rule had 3 percentages, 68, 95, 99.7. Cheby believes there's only 2, 75, 89. That's the difference between empirical rule and Cheby. All right, so let's do an example, and you're gonna do the same thing. You don't have to memorize these formulas, but you do have to memorize the 2 percentages. And those are set. Those are set, just like the empirical rule. You cannot change these. These are set in stone. You can't change those. We're gonna do the same thing as we did with the empirical rule. We're gonna label our mean, and we're gonna go ahead and start adding standard deviation, but just make sure that when you go back and you're dealing with Cheby, you're gonna mark these numbers off. Those don't exist. All right, so let's do one. Let's do an example from the book. And the one in our book is on page, and so I can find it. It is on page 'Nope. There you go. Number 43. Okay, so let's look at it. So 43 says, based on data set 1, body data, in Appendix B, blood platelet counts of women have a bell-shaped distribution with a mean of 255.1. All right, so here they're telling us that the mean is 255.1. So I'm going to write that down. We're doing number 43 from section 3.2. So my mean is 255.1. And it also says that the standard deviation is 65.4. 65.4. And this is on page, sorry, I forgot to tell you the page number is page 111. Right, so they're giving you the mean, they're giving you the standard deviation, and they're asking you to apply Cheby's theorem. Okay, so we're applying Cheby's theorem. It didn't say bell shape. It said Cheby. All right, so I'm gonna draw my curves. They're giving us this, and I'm going to draw my curves. Okay, in the middle, I'm going to put my mean. My mean is 255.1. 255.1. I made it too close. 255.1. All right, and I'm going to go ahead and start doing like I did with the with the empirical rule, right? So what do? How do I figure out these tick marks? So I'm going to add as I go right. I'm going to add 65.4 as I go forward, right? So let me take out my calculator, and I'm going to add 255.1 plus 65.4. I get 320.5. So this is 320.5. Next one, I'm going to add to that another 65.4. I get 385.9. Add another 65.4. I get 451.3. Right? You barely see that thing. Again, 320.5. Okay. Now, if I want to figure out this side, I'm going to get my 255, and now I'm going to subtract. I'm going to subtract 65.4. So 255.1 minus 65.4. I get 189.7. Subtract another 65.4. 124.3. Subtract another 65.4. 58.9. Okay. And I'm dealing with Cheby, so that tells me I'm going to block. I'm going to cross that out. That doesn't exist. Right? He doesn't believe that those exist. So now I have my curve, and now I'm going to fill in my little boxes. So this box from the 124.3 to the 385.9, that percentage was 75%. That's what he believes in. And the other last two, that one with the ends, was the 89. I'm going to put it there, 89.89%. Just 89%. 89%. All right, now we have my labels, my horizontal scale labeled. I got my percentages. Let's go back to our questions in the book. Let's see if we can answer them. So, the last part says, using Chebyshev's theorem, what do we know about the percentage of women with platelet counts that are within 3 standard deviations from the mean? What is the percentage of the number of women who have platelet counts that are within 3 standard deviations of the mean? All right, so let's go back to our graph and see what we can figure out with that. I want 3. I need to know, is it 75 or 89%? I need 3. Oh, okay. So the 3 are the ends. The 3 in the ends are the 3 standard deviations of the mean. That equates to 89%. Going back to our graph, right? The 3 in the ends is 3 standard deviations from the mean, the ends from our graph that we produced, right? So that's where we got 89%. Okay. And B, what does B say? They want to know what are the minimum and maximum platelet counts that are within those 3 standard deviations from the mean? So they want the actual numbers that give you the places where the 3 standard deviations are. So let's go back and look. So my 3 standard deviations from the mean are 58.9 and 451.3. And that's it. The end.